Hi everyone. My name is Adina Pusok. I'm happy to present today some of the results from numerical models, primarily on melt transport across the lithosphere. And as Sasha mentioned, this is going to be applied to the Turkana Depression. So the Turkana Depression is this low-lying region in the East African Rift System, located in between the Ethiopian Plateau to the north and the East African Plateau to the south. And as already the topography map highlights, is an interesting area. And I'm going to focus my work primarily to compare the Ethiopian Plateau with the Turkana Depression. So the Ethiopian Plateau in the north is an uplifted region. It shows the so-called magma-rich rift. So we have a narrow rift valley, which is bounded by faults, and we have active volcanic centers in between. And also studies in the main Ethiopian rift suggest that the strain is mostly accommodated by magmatic intrusion. To the south, the Turkana Depression shows some contrasting features. So first of all, as I mentioned, it's a low-lying area. It's about 300 kilometers wide, but faulting, seismicity, and volcanic centers seem to be widespread, as illustrated over here. And also strain is largely accommodated by faulting and stretching, at least until the last few millions of years. So in terms of rift architecture, the Turkana Depression has been neither magma-rich or magma-poor. And as I will show, its current models cannot explain the deformation. So, but for some of the first ideas to explain the difference between the Turkana and Ethiopian Plateau has been the suggestion that maybe Turkana form above a heterogeneous plume or above a gap between two plumes, and therefore it lacks dynamic support. However, recent geochemical and geophysical data suggest actually that, or support a single plume hypothesis, therefore that the mantle beneath both Turkana and Ethiopian Plateau seems to be hot, partially molten, and buoyant mantle. So this initial idea seems to be unlikely nowadays. More recent observations, primarily coming from the large project called TRAILS, led by people from Imperial College London, they do highlight some interesting observations. So for one, we know that the crustal thickness beneath Turkana is much thinner. It's 20 to 30 kilometers compared to the Ethiopian Plateau, which is 30 to 40 kilometers. There has been seismicity follows a similar trend, but we also start seeing some regional variations, which are highlighted in the study by Musile and co-workers. What they observe is that the Turkana Depression can be split into different areas, primarily Zone A to the north, where the deformation is diffuse. But in Zone B, strain seems to be focusing into the Turkana Rift Valley. So there is definitely some transition, but if you take the area as a whole, it's still quite different compared to the Ethiopian Plateau and the Kenyan Plateau below. So some of the ideas to explain this diffuse deformation and also why it has like such a thin crust, that could be due to a weakened lithosphere. And the weakening can also be due in turn to a magmatic intrusion during the flood basal stage, but also due to inherited damage from multiple rifting episodes. Both of these ideas can produce thin, broadly distributed faulting. And there are different models. So, for example, the early model from Buck 1991 that shows distributed deformation and producing a white rift mode, shown here, can be due to a hot crust, but also more sophisticated 3D models by Sasha, Corti, and co-workers that suggest that Turkana could be due to some inherited damage from before. Some of the problems with this models is that they can't explain the diachronous evolution, and that means that there seems to be a west to east migration of magmatism and sedimentary basins in Turkana. And also, since there is this migration of magmatism, these models do neglect magmatism, which I'm going to address here. So while I'm not discrediting this hypothesis, actually I'm going to use it, there are some limitations to this, or some process that we don't fully understand. So we need to also look at the tectonic and magmatic history of the area. So if I draw a timeline over here from the arrow pointing to the present day, and we're going to the tectonic, rifting, and magmatism, we know that Turkana experienced 3 episodes of rifting, for the first in the Cretaceous, the second in Paleogene, and the more recent ones in the last 20 to 25 million of years. When it comes to magmatism, we need to take into account that before any basalt magmatism in the area, Turkana Depression experienced already 2 episodes of rifting, which was followed by, so the first flood basalt magmatism occurred at around between 45 to 35 million of years in southwestern Ethiopia, and up to 5.5 degrees north, which is highlighted here. So below this region and in most of the Turkana, there hasn't been, or there has been limited magmatism. A second episode of flood basalt magmatism, and the main one in the East African rift system, which occurred in the Red Sea, the Gulf of Aden, and Ethiopian plateau, occurred between 32 and 25 million of years. And it's highlighted here in this figure from Rita Konodis and co-workers with black contours. This is the outline of the flood basalt magmatism in this area. And in red, we see the most recent one. So we see this localizing from in the interior of the Rift Valley, in the main Ethiopian rift, with more progressive age. And this evolution of the formation from widespread to more focused into the Rift Valley also fits our understanding of rifting. So in this cartoon from Biggs and co-workers, from bottom to the top, we have increasing rift maturity, and we go from a flood basalt stage where magmatism heats and weakens the lithosphere, and then the formation focuses into a narrow valley. However, this model doesn't fit Turkana, and I will explain why. First, because in between, since 35 million of years, we've had magmatism in the area. However, they've been more pulses of magmatism, including breaks of 5 to 7 million of years. And also to present day, we have more localized volcanic centers and magmatic intrusions, which are summarized in this geological cross-section from Morley 2020. So we have volcanic centers. We do know that there are intrusions, but most of the literature agrees that neither the tectonic or magmatic extension beneath Turkana have developed to the same extent as the one in the Ethiopian plateau. So my main question here is why Turkana developed differently compared to the Ethiopian plateau. And to simplify the picture, we've seen that there are quite many complexity to the area. These 2 areas can be simplified in the following way. The Ethiopian plateau is a magma-rich type rift and is consistent with our understanding of rifting. But the Turkana Depression, is it or is not a pore rift? And if yes, it occurred in rifted crustal lithosphere. So if this is the picture, the following questions: why hasn't Turkana developed earlier into magma-rich rift despite a thin lithosphere? Why hasn't it experienced more volcanism? And also an unanswered question is, how can widespread faulting and magmatism coexist in the same area? So in my study, I will hypothesize that all these features can be explained by that lithosphere thinning and weakening in Turkana relative to the Ethiopian plateau have influenced magma transport, magmatism, and subsequent rift development. And the scenario that I will consider is to investigate magma transport across the brittle ductile lithosphere in the East African rift system before at early stages of rifting. And this is I'm going to take a simplified view of considering the following scenario where the Turkana has a thinner brittle layer compared to the Ethiopian plateau that has a thicker brittle layer. And I will consider that both areas are underlain by one mantle plume, so there is a source of magma, and I will consider how magma reaches the surface. In terms of rheology, this can be captured as a strength depth profile for shear deformation and volumetric deformation. And case 1 for Turkana is shown as a thinner elastoplastic or brittle layer, which transitions into a more ductile mantle or ductile layer. So in this study, I will consider 4 rheological test cases which take into account this strength depth profiles, but I will focus primarily on this case TD, which is analogous to the Turkana Depression, and case EP, analogous to the Ethiopian Plateau. And I will use numerical models, which use a recently developed theory of poroviscoelastoviscoplastic flow. I'm not going to go into much more detail, but on the left is highlighted the conceptual model of what we were trying to do, and that is incorporating magma transfer with the ductile brittle deformation of rocks. But what we're actually doing, we're solving for the theory of two-phase flow of partially molten rocks. We're solving for conservation of mass, momentum, energy. We also include a free surface and the complex rheology of rocks. And that is we're incorporating the viscous, elastic, and plastic behavior of rocks.
Dina, you had 11 minutes now.
Thank you. And the model setup that I'm going to consider is a typical cross-section of the lithosphere, which can be put under extension. And we're going to test how a body of partial melt in a depth rises to the surface. And I'm going to test the different rheological cases and also 2 types of experiments of no tectonic extension, so prior to rifting, and with tectonic extension or early stages of rifting. So going straight to the results, I'm going to show 2 cases, case TD with a thin brittle layer on the left and case EP with a thick brittle layer. On the top, I'm showing porosity maps, so the amount of magma in the system, and on the bottom, I'm showing plastic strain or brittle deformation. Both have the same time frame, so I'm just going to play the movie. And what we can see is that KCP shows fast magma transport, and actually magma reaches the surface 4 times earlier than in case TD, which is still going. However, we do see some interesting features in terms of style of transport, so porosity waves, and also vertical and horizontal tensile failures. We also obtain by different styles of transport by varying parameters. So, for example, by varying the volumetric strength of rocks, we obtain a widening of the magma body at the brittle ductile transition. But we can also obtain even more drastic contrast. So, for example, by actually increasing the amount of magma in the system and tuning a technical parameter, we reach the fastest ascent rates, while for case TD, we actually have magma arrested in the crust. Even if we obtain a number of different results, we can still be systematic by assuming that the style of magma transport is controlled by the deformation at the tip of the rising magma body. And by doing this analysis, we can detect the ductile brittle transition and a lot of other things that characterize our results, but I'm not going to go into detail. I only want to summarize in this slide a number of numerical simulations. And here I've varied the initial magma volume in the system, so going from a little bit of magma to a lot more magma in the system, and that means there's more buoyancy. And on the left, we have the thickness of the brittle and ductile layers, and on the right, we have the ascent rates. And the important things to take away from here is that case TD has a thinner brittle layer compared to case EP. And on the right, we see consistently that Turkana depression or cases related to DD are much slower compared to the Ethiopian plateau. So case TD is considered slower, despite having a thinner brittle layer. And one last experiment is this transparent under extension. So the same simulations, but now I'm imposing a background strain rate. So I'm just going to play the movie. And what we see is some very interesting features. But first, we do have faster ascent rates in both cases. But we do see a localization of surface faults in TD. And very importantly, we do not notice them in KCP. And to long story short, we do observe a mixed magmatic tectonic extension for case TD, while for EP, we see a fully magmatic extension. And to summarize, we are showing that magma extraction across a thin weakened lithosphere is slower than across a thick elastic lithosphere. We do show how rheology controls the style and the rates of magma transport. And we tested the hypothesis that a thin but weakened lithosphere beneath Turkana acted as a barrier for maltransport, and this impacted the reef development. And I'm happy to discuss more, especially the implications of this model, primarily that it is on one hand consistent with forming the diffuse deformation, so having a mixed magmatic and tectonic mode, but also it could also help with explaining the diachronous evolution or the migration from west to east of magmatism and deformation in the area. But something to keep in mind is that even if I'm showing a new model and potentially with complex physics, it is still a simplified model and also lithospheric structure, and some of the features we can't explain for Turkana. However, it is a one step forward into actually understanding magma transport and storage in the lithosphere. So with that, I thank you for your attention.
Thanks a lot, Adina. These are amazing results, and there are so many things that one can discuss, but we only have time for one question. And if someone has a question, just raise your hand, please, or make yourself known in the chat. Derek.
Thanks. Very interesting talk. I didn't quite. What did you base the depth of the brittle ductile transition in the two models? Is it based on seismicity, or is it? Yeah.
That's a very good question. So I want to highlight. Let's just go hopefully back. No. I guess okay. I do have a slide over here. Is this visible?
Yeah.
Okay. So I do consider a very simple model, as I showed, like that, just having a brittle layer lying on top of a ductile layer. This is the simplest one can do with models. But I do model it based on the study from Ogden and coworkers, and also a more recent study by Musila, which also shows the seismicity follows the crust thickness variations in the area. Now, there is a bit of a mismatch between what we see present day and what was happening in the past about 25 million of years ago or more. But we do know that Turkana has been rifting two times prior to the most recent. So we do know that we have to consider somewhere a reasonable depth of the brittle ductile transition.
And then for the Ethiopian rift or the Ethiopian plateau, where did you get the depth for the transition?
So again, this study suggests like a crustal thickness of 30 to 40 kilometers. Of course, this is not necessarily a proxy for the ductile brittle transition. It's just like a kind of a rule of thumb. But this is something we can do with models, right? We can vary that depth. And actually, the models that I've shown only has about a 10 kilometers difference. So the difference between these two is only 10 kilometers. But with more, I've run some more models where I varied that variation, and we still obtain the same results.
Yeah, thanks.